into those the components of the fired heaters, and especially simple heaters. I do not intend to talk about any kind of reaction heaters like reformers or olefin crackers. Not necessarily olefin, all kinds of crackers or reaction heaters. I just want to talk about simple heaters today, and if possible later I will talk about reaction heaters. So the second part of my presentation is dedicated to the introduction of the different components in process heaters. And the third part is dedicated to the design criteria, both from process side of view and mechanical and structural side of view for these components. We go deeper into components. I think as my own idea, this is the most attractive and exciting part of my presentation. So as you see, the flow of the presentation is designed for very, very low experience guys to enjoy that. And it finishes with a little bit considering to the points of view for much more experienced guys. So let's just start with this. There are three other parts, three minor parts which I added to this presentation. First of all, I added the introduction section for my company. Second, I introduced myself to you. And at last, at the end of all the slides, I introduce some good reads, good books and handbooks and standards for you to read more on this area in this topic, and use it while either you are working in vendors, manufacturers, consultants, clients, or MCs. That would do good for you, and hope you will enjoy and use that. So let's start with our presentation. I cannot make this PowerPoint full screen. It has some issues, so hope you can see my screen, and it's okay for you to see the screen in this size. Can everybody see my share the screen? If okay, please raise your hands or say something that I understand you already have my screen. Okay, thank you. Good. So process direct fired heaters, an introductory lecture presented by me October 2, 2024. What we're going to discuss today, I've discussed most of the structure I have designed here. First of all, I introduce, there's some introductory sections, then I go through definitions, then I review the names and the job of every component inside the furnace. Then I go through design considerations from different aspects. And after that, at the end, I give you some references if you wanted to read more on the topic. Okay. First of all, my company's name is F.Naghsh Heat. What do we do here? We offer engineering and supply services to companies active in oil and gas and procurement, pharmaceuticals, automotive industries. While doing that, while offering engineering and supply services, we are very, very aware of our environment. So we are very environmentally conscious and provide more sustainable energy solutions. How do we do that? We do that in two forms. To sustain our environment, to keep it clean, we do two things. First, we reduce the fuel usage in combustion equipment. This is one way of conserving nature. And second, we reduce the pollutants, which is a very, very important topic in today's industry, and geopolitically, it is very important. So if we do that, if we control the energy usage, resource usages, and also the pollutants, we can cut operational costs for in-service plants by providing optimized solution by doing these two things, reducing energy combustion and pollution penalties. Uh, you know that most of the combustion equipments in plants uh, hold the most energy consumption uh, costs inside a plant. So if uh, if a
مامان
plant is able to
صندوق
reduce
عیار
its
که
energy
خریدم
resource energy resources usage, it will
یک و
have a
500 امروز
significant
سود
amount
کردم،
of
یعنی
uh,
رفته
operational
روی
cost cut.
گرون شده
So
یعنی.
a lot of money will be made during this process. So if we go more into the depth of this matter, how do we do that? We do engineering and design, we optimize the processes, and also we do the personnel training. We also manufacture the equipment we design in conjunction with very big names inside Iran, which the products are fixed equipment like a storage tanks, shell and tube exchanger, pressure vessels. Uh, we supply flares, burners, and pollution control systems, combustion, gas and air preheaters, and also waste heat recovery systems in conjunction with our European and Chinese partners. So this is what we do. And last but not the least, I am the CEO of this company. I have a master's in mechanical engineering, applied design, a bachelor's in mechanical engineering, thermofluids. Also, I have 12 years of experience backed up by a perfect engineering team, which have cross-industry experience, me, myself, specifically in thermomechanical design. Okay, this was the introduction. So let's start with direct fired heaters. Okay, first of all, the definition of direct fired heater. You see the title. I have written direct fired tubular heaters definition. It shows that there is tube inside. Why is it important to note that it is tubular? Because there are a lot of furnaces that do not contain any sort of any sort of tubes. For example, like cement furnaces, like incinerators, like direct reduction iron, reduced iron furnaces. So we are here tonight, we are talking about a very specific kind of heater, which is called process heater in the process industry. So what is that? It is an insulated enclosure. What do I mean by insulated enclosure? By insulation, I solely mean the refractory inside the casing. You may have an equipment that is insulated from outside due to different reasons. I don't want to review the reasons. Maybe it's for the process, maybe it's on a stack, it is insulated as the process department needs to make sure that the hot gas exits the stack, or maybe for personnel safety from the outside, so the equipment is insulated from outside. Another kind of insulation, or let's say better to say protection, is fireproofing up to certain levels of the equipment in case of hazards, fire hazards. I don't mean those kinds of insulation or protection. I only and solely means insulation, which is meant refractory from inside the casing. Another implication of this matter shows that when you insulate something against a high heat conduction, you can reduce your cost by using a less exotic metal for the casing. For example, you don't need to use gold or nickel alloys for the body of that equipment. You can use simple carbon steel. and by simple carbon steel, I mean a structural carbon steel as the casing. So you can reduce the cost by insulating the enclosure from inside. So it is also an enclosure. Keep in mind that it is an enclosure. It is not a pressure vessel. Uh, uh, it is enclosed, but it has way to the around atmosphere. So these two words have a lot of meanings. It is insulated. Its pressure is something near atmosphere pressure. Another point in definition of a direct fired heater is that it burns or combusts fuel. Yes, through a burner, it uses the fuel to produce heat. You may ask the difference between burning and combustion. Uh, if you refer to the dictionary, you see that burning has a lot of light emittance, and combustion is a more general word to reaction with oxygen. So you may ask, do we have any kind of combustion that doesn't emit light? Yes. Normally, hydrogen combustion is a sort of burning that you cannot see. So because it doesn't emit any sort of visible light. So it implies that we can have a flame inside the direct fired heater, which may be visible or maybe not visible. So it means that it burns or combusts fuels, any sort of fuel. We have natural gas. Natural gas can be as a source of fuel. We can have liquid fuels like LNG, and also we can have solid fuels. All of them are possible to use
امروز
for
گیر داده بودم
providing
به
a heat
من که
source for a direct fire heater.
شوخی با من
Also,
میکردن که
another
نمیدونم
another
ازدواج
uh,
معیارات چیه و نمیدونم
point
میشن
that
دوست
is
داری اونو
very
دوست داری.
bold in definition of direct fired heaters is that the heat that is
آره
produced
متاسفانه
is transferred to the process fluid. So it is transferred and it
بعدا ما
moves.
حسرت
See the next
میخوریم که
one.
چرا
Process
یه
fluid
وقتا اونو
move
تلف کردیم.
inside the tubes. So the heat is generated, the heat is emitted, radiated, or convected to the
نه
tubes,
بعضی جاها بیشتر
and
کار.
it is then transferred to the fluid
من این
inside,
پروسس خودمون خیلی
and
کار میکنم.
the process fluid inside, which typically is a stream of hydrocarbon, takes the heat and
ها
runs through the heater and then exits the heater. So these two last sentences
آره.
give two direct results. First of all, if you have a heater, if you have a furnace
من پی ام پی اون
that for
بگم
any reason doesn't have any
پروژه
kind
خیلی
of
کار میکنه.
fluid
پروژه
inside
از
the
همه
heater,
بخشا فشار روش
if you
بیشتره.
start the burners, the tubes will eventually fail because the heat generated inside the furnace is not carried away by a process fluid.
خود
And
پروژه
the other
بری
thing that
مهندس پروژه بشی
we
اونجا
can
خیلی
conclude
پیگیری
from
باید
these
بکنی.
two
خیلی.
sentences is that uh, if inside the tubes of a heater a fluid exists, but it does not move, it is not able to carry away the heat. So in that case also, the tubes or the furnace refractories itself uh, will fail. So these are the conditions for a heater to be a direct fire tubular heater. Okay. Okay. So now that we have a grasp of what a fired heater is, uh, let me. Someone might ask, what is? Someone might say that it is a heat exchanger. A fired heater is a heat exchanger because it exchanges heat it exchanges the heat that is produced by the burners. Yes, this definition is also correct. Direct fired heaters are a sort of heat exchangers. Uh, but we also have other sort of heat exchangers, like shell and tube heat exchangers, like boilers. They are also a type of heat exchangers. When do we use a fired heater? Uh, the answer is when you want to increase the temperature or transfer a large amount of heat to a fluid, we use direct fired heaters. Uh, Someone might say, what about this, for example, shell and tube heat exchanger? Uh, in shell and tube heat exchangers, uh, you have to have a high area of heat transfer to transfer that amount of heat which is needed for our, for example, hydrocarbon stream. And we need, for example, a lot of steam, utility steam, high pressure steam, to make that heat transfer possible. So up to a threshold, it is possible to have a shell and tube heat exchanger as the exchanger of choice. For example, up to 100, 150 degrees Celsius. But above that, uh, when larger duties or high process temperatures, starting from 300 degrees Celsius above is needed, uh, we have to use a fired heater uh, because of the heat available by the combustion of fuel, and also by the limitations of the footprint, so that we cannot use a shell and tube heat exchanger. These fired heaters, these direct fired heaters, are designed as per API, the famous standard API 560, and the European equivalent of that standard is DIN 4754. And also note that fired heaters have safety problems because the casing lives in an atmospheric condition. It is considered an open flame. So we need to keep that safe. And if you have a plant that prohibit the use of an open flame, you cannot use fired
آه من
heaters, or
یکی
you
شو
have to
بیشتر
do
نمیتونم
something else to
بخورم.
provide that kind of heat to your stream. I said that the direct fired heaters are designed per API 560. I want to take your attention to the first paragraph of this standard. I have highlighted with green color here. Let me read that for you. This standard specifies requirements and gives recommendations for the design, material, fabrication, inspection, testing, preparation for shipment, and erection of fired heaters, air preheaters, fans, burners for general refinery purpose. This standard, now the explanation. General refinery service. What does general refinery service mean? Uh, it is an explanatory sentence for the previous sentence. This standard does not apply to the design of steam reformers or pyrolysis furnaces. We have many instances that my colleagues call me and ask me if we can use this part of API 560 as a reference for steam reformers. API 560 very directly prohibits you from using this standard for reaction furnaces like steam reformers or pyrolysis furnaces. So although it has very quite useful things that can be used inside those reaction furnaces, like the refractory section, it is generally not applicable to those type of equipment. So be aware that the main standard we are referencing is only for simple heaters for general refinery services. Okay. So where is a direct fired heater used? I want to point out that the heaters that have a reaction, the chemical reaction inside them, and also the heaters which do not have a chemical reaction, they are all called direct fired heaters. So you see that most of the usage of direct fired heaters are in refineries like CDU, VDU, hydrotreaters, and
نه
coker plants.
جانم
And also in petrochemical plants, we have reaction furnaces
حسن
like
جان
olefin plant, crackers,
جانم کربه
and steam reformers
تازه
in
هم نهار
methanol,
خوردم ساعت یک
ammonia,
نهار
and some plants that produce hydrogen
بذارش نصف که رفتم
with steam
برگشتم
reforming method. So steam
نه میره
reforming and cracking are the major reaction furnaces. And now that I have decided, I've described the two types of furnaces. We have a slide for it here. As my point of view, the heaters, the direct fired heaters, are divided into two major subsections. First of them are simple heaters, and the other one are reactor heaters. What are simple heaters? You see the picture here. It can be cylindrical. This part can be cylindrical, or it can be a box type heater. So where are they used, and what do they do? These simple heaters, what do they do? They raise the temperature of the fluid. The fluid may change phase or not. Maybe you have a liquid that send it into the heater, and the outlet is also a liquid. Maybe you send the liquid, you receive a two-phase fluid. And maybe you send the liquid and then you receive a gas fluid. So this is the work of the simple heaters. They increase the temperature. The phase may change or may not change. This is the performance of a heater. This is what a simple heater do. In contrary, not in contrary, in conjunction with these simple heaters, there are reactor heaters. Like their counterparts, they transfer heat to the fluid. The heat initiates and drives a chemical reaction. So a chemical reaction happens in a reactor heater. As the name implies, it's a reactor heater. Usually in presence of a catalyst. It means that to drive that reaction, the temperature or the heat that is provided by the burner is not sufficient. Sometimes it is not sufficient. So you need a catalyst to reduce the temperature or increase the rate of that reaction in the temperature that the burner has provided. So the heat is transferred to the fluid. The heat initiates a chemical reaction. This chemical reaction, to complete, may need a catalyst or not. The instance that a catalyst is needed is steam reforming. Steam reforming needs catalysts. Or a fired catalytic cracker. We have crackers that use catalytic firing. Also, we have olefin furnaces that are thermal crackers. They do not need any sort of catalyst, but still a chemical reaction happens. That chemical reaction is thermal cracking, which I may go through these two types of reaction heaters in future seminars. But my purpose tonight is to talk about simple heaters. Okay? You see here two pictures of a simple heater, which I said it is vertical cylindrical. As an abbreviation, it is known as VC, vertical cylindrical heater. And the other one, is EDC, Axens ethylene dichloride cracker. It is a sort of cracker, and it converts EDC to VCM, vinyl chloride monomer, and it is a key building brick for producing PVC, polyvinyl chloride. This is also a cracker. It is taken from Axens websites, and the license is for Axens company. Okay. Any questions so far? Anybody? Everything clear? Okay. Let me tell you that if you have any questions that you may forget, you can write it here on the right in Zoom. There is a chat window. You can write it here between the slides. I come and check these chats, and I will answer you. Those of my friends who are comfortable writing in English, it's okay. And those of my friends who are more comfortable in Persian, they can write in Persian, and I will answer them both in Persian and English. Okay, let's get back to business. Okay, now that we understood that we are talking about simple heaters, we return to API 560, figure 1, and review the different geometries that can exist for a simple heater. We have 6 major geometries for a simple heater. From now on, I call it furnace because you have understood what I'm talking about, and furnace is easier to pronounce. So I'll talk about furnaces. Okay, type A, box heater with arbor coil. You see it here. These geometries are based on this box below the heater. It is called the radiant section. We will go through it. We'll talk about it, why it is called radiant, what happens inside it. But for now, keep in mind that the geometries are categorized based on the geometry of the heater is categorized based on the geometry of radiant section. You see that the difference between these heaters are the geometry of the lower side of the heater. The burners are installed inside the main heat transfer happens inside the radiant section, and due to change of geometry, the tube's configuration here also changes. So let's start with type A box heater with arbor coil. These coils that looks like an arc, and you see the headers, inlet headers and outlet headers below the heater. And the radiant section looks like a box. You see the section as a rectangle. So suppose it is inside the plane of the computer. It is a rectangular box. So it is a box heater with arbor coil. You see, this geometry, this configuration of the heater is, I think, as my experience tells me, this is the lowest duty available as a heater. When we talk about other heaters, we can increase the duty, or vice versa. Better to say that when the duty increases, you have to change the configuration of the heater you're using, because for example, for this arbor coil, it is not possible to have, for example, 12 megawatts of duty, and for helical heaters, it is not possible to have, for example, 20 megawatts of duty, because because of the limitations on manufacturing and installation of the heater. So consider these geometries as by increasing the A, B, C, D, E, F, the duty normally increases. Okay, we talked about type A, and type B is a cylindrical heater. Consider this part as a cylinder. This is a conical reducer, and the tubes are designed in helical form. They look like a helix, and so you see that the manufacturing cannot bear a very high diameter heater. The next one is cabin heater. What is the difference between cabin heater and a box heater? You see this section, this inclined section, but the box heater has 90 degrees angle, but the degree here is not, the angle is not 90, it is more than 90 degrees. So it is a cabin heater with horizontal tube coils. Assume that the tubes inside the plane of the heater uh, are perpendicular to the plane of the your monitor, your computer. Also, increasing the duty, type D box heater with vertical tube coils. Uh, the tubes are vertical here, they go up, they have a return bend, they come down and they go up, all in the plane of of your computer. Uh, where is this type of heater used? It is where you have a higher duty comparing to the previous types, and also when you need a more uniform heat distribution. The burners are installed uh, in front of the tube, and you have a better heat distribution. So the next one is cylindrical heater uh, with vertical coils. It is also the cross section is you can see it as a rectangle, but in 3D it is a cylinder. And the other one, box heater with horizontal tubes. They are the same, but the arrangement of tubes change. Also, you install the burners between the two tube rows. Yes, uh, this also you see that the configuration of the tubes are becoming more and more. The number of tubes are becoming more. So it implies that the duty is increasing by going from left to right. So these are the normal configurations that is recognized by API 560. Okay. 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 Now we reviewed all configuration possible for a direct fired heater. Uh, let's go and review the major components of a furnace. Every furnace has every direct fired heater, simple heater, and now I call it a furnace. Every furnace has three major components. The first one, as I am showing here, is the lowest compartment, which is called the radiant section. The second part, the second major part, is called the convection section. And the third part is the stack, which guides the flue gas outside the furnace. Okay. So radiant section, convection section, and the stack. There is also a gap between stack and convection section, which is natural when you want to connect a circular cross section to a rectangular cross section. You need something. You need a transition piece. It is called the bridging section. In operation, this will cause a few problems. I will go over it, but for now, we have three main and major compartments. First of all, let's talk about radiant section. This section is called the radiant section. I think the name implies that what a radiant section is. Radiant section is where the heat is transferred to the process fluid, mostly via radiation. Let's read these 4 points. Radiant section, which is also called a firebox, is the primary heat transfer zone. Most of the heat is transferred inside the radiant section. Heat transfer mode is mostly via radiation. Yes, the name implies that most of the heat transfer is via radiation. Also has various geometries. we talked about the possible geometries available here, so we will not go over it again. Also, burners are installed in this section. Yes, we cannot install burners in convection section or stack or somewhere else. I am talking about, remember, I should remind you that I am talking about simple heaters. There are configuration in reaction heaters that some burners are installed before the convection section in reaction heaters. But for now, I'm just talking about simple heaters. So burners are only installed in radiant section, either in the bottom of this radiant section or on the walls. So this is the radiant section. Now I want to go over this sentence. Heat transfer mode is mostly via radiation. You may ask why I have used the word mostly. Why is it called mostly via radiation? To understand this, you need to have you need to have an understanding of the heat transfer modes inside inside a furnace. Listen carefully. We have three heat transfer modes inside a furnace. In every part of a furnace, there are three possible heat transfer modes available. First of them is radiation. What kind of radiation? Consider a burner here. The burner combusts fuel, and the products of combustion are flue gas. The flue gas is released inside the firebox. It is very hot, and when it comes here, it radiates its heat to the tubes, and the tube transfers it to the process fluid. So the first mode of its heat transfer is radiation from flue gas to the tube. Also, this flue gas passes from between the tubes and increases the temperature of the refractory on the walls and floors. So this flue gas increases the temperature of the refractory. The refractory also radiates heat to the tube and the tube to process fluid. So our second mode of heat transfer is radiation, but from refractory to the tubes. So we have two modes of heat transfer which are radiations. One from flue gas to tube, the other refractory to tubes. Also, the flue gas it transfers its heat via convection to the tubes. So first flue gas radiates to two tubes, then refractory radiates to tubes, and then flue gas convects its heat to tubes. We have these three heat transfers in every part of this furnace. You may be asking, what about conduction? Many experiments have been done, and these experiments have shown that the effect of conduction to tubes is negligible. So again, we have three heat transfers mechanisms that are active inside the furnace. And now, in radiant section, most of the heat transfer is done by radiation. The name implies that the radiation mechanism is dominant here. And also the convection section implies that the convection mode is dominant in convection section. So that's why I use the word mostly via radiation, okay? Now let's move to convection section. This is the secondary heat transfer zone. And yes, the heat transfer mode is mostly via convection, increases the efficiency of heater, and no combustion and flame should happen. Uh, Suppose or consider the convection section. No, suppose this. You have a hot flue gas uh, coming out of the radiant section of the heater. It is still hot. It has energy. And if you send it to atmosphere, you are wasting a huge amount of energy. As this was the case, for example, 100 or 80 years ago in the United States. For example, in 1940 or 1950, there was no convection zone inside furnaces that were designed in the United States. So by convection section, we are designing an economizer to use the waste heat energy to the benefit of the process fluid. So consider this section, which we call it now as convection section, as an economizer for the furnace. This has been put here to reduce the amount of waste energy that is sent to the atmosphere. So, if you absorb more heat from the flue gas, you're actually increasing the thermal efficiency of the heater, and also reducing the exit temperature of the flue gas, and also you are doing good to the atmosphere and you're being atmosphere friendly. Also, no combustion or flame should happen. Okay. Why is that so? When you design an economizer for a heater, to increase the area for heat transfer, you may use extended surfaces tubes, fin tubes, for example. Fin tubes, the fins of fin tubes usually have a different metallurgy than the tube which is the base tube of that section. So if somehow any sort of combustion happens here in the convection section, the fins do not have the capability to withstand the flame or combustion that is happening there. So the fins will melt, and they will clog to each other, and they will close the pathway of the flue gas, which is trying to exit the furnace. So in any scenario, there should be no combustion or flame in the convection section. You may ask, is it possible to have a combustion or flame inside the convection section? We do not have a burner there, so naturally we won't have any sort of combustion or flame there. Yes, it is possible. In some scenarios, which is not the topic to discuss for this webinar, in some scenarios, in restarting the heater, in startup sequences after an unsuccessful shutdown, you may have some hydrocarbons stuck here. And if you increase the temperature and introduce air here, you will have an explosion. You will have a flame. You will have combustion here. So that flame may damage the tubes, the metallurgy, the fins, the extended surfaces, and cause problems for the heater. So yes, it is possible to have a combustion here, and it is caused by bad operation of the heater. We should avoid that situation, and a good operator is a person who knows what is going on exactly inside the heater by reading the analyzers, reading the sensors, and understanding the situation. Although some tries are made, some attempts are made to for BMS, burner management systems, to make sure that every hydrocarbon here, every possible hydrocarbon here, every combustible here is purged off before a restart. and this has significantly reduced the amount of mishappenings inside the heater. But yes, it is possible, and we should totally avoid that. It's not a good thing in convection section to have a combustion or flame. Okay, the other major sections are fans, stack damper, burner management system, burner instrumentation, and refractor. Okay. I forgot to talk about stack. The stack, when the heat is transferred fully with the convection, with the tubes, with the extended surface tubes inside the convection section, the stack helps the flue gas get out of the heater. How does the stack do that? The stack does that by a phenomenon called the stack effect, and this is done by the stack effect. And the flue gas, alongside with its energy and the stack effect, uh, goes out of the furnace by the help of the stack. We will talk more about the different components more in the design criteria. Okay. Okay. Mr. Kui, how much percentage heat transfer in radiation in furnace? I will cover it in next slides. About 60 to 70% of heat transfer is performed in radiation section. Mr. Rahul, can helical coil heaters are designed for two-phase services, and can we design it with more than one? Yes, it is possible. No, it is not. Yes, helical coils. Helical coils cannot be designed with more than one pass. I haven't seen that, and I cannot figure out how it is possible to do that, because the coil is uniform and it has no branches, so it cannot be designed with multiple passes, I think. And for two passes, yes, it can be designed for two passes, but I haven't seen such a heater, but it depends on how much the process fluid which enters the coil has energy, and how much energy it will need to, how much energy more it will need to change states from one phase to two phases. So it totally depends on the process. For steam superheaters, what standard we use, Mr. Kui, I will check it and tell you later. It is not covered by API 560. I think it was 534. I must check. Okay. So okay. I have zoomed a little bit on this. How much time? Yeah, it's okay. One big thing happened. I forgot to record the presentation. Okay, we'll record the presentation after the break. Okay. Let's have a 15-minute break, and I will continue the explanation more on this figure. Thank you. We'll get back in 15 minutes, which is 7:11 p.m.